Is this on? Ah, this is on. Mm. Are we? Should we start? You think? We start? Okay. So I'm gonna start. Can I? So first of all, if you, I'm going to walk through this myself on the projector, as I said. I'm then going to send a link to Ben where it's like a documented version of the same thing, so you can click through it in your own time. Given that the Wi-Fi is not greatest here, maybe if we don't all try it at the same time, it's going to work. But I thought that it's better if I walk through the code myself, and I'm going to rewrite some of the code so that you can follow along with what I'm writing, hopefully. And before I start, can I just ask who's familiar with Python? Okay, fairly. Who is not familiar with Python? Okay, so there are a few people. I think that's sort of what I expected. It's going to be in Python. It's going to be on Colab. For those of you who don't know Colab, it's great. It provides you this IPython or Jupyter notebook-like experience, and it's hosted on Google. And you can actually get free hosting from Google. So if you just log into colab.research.google.com or something, then you can just start your own IPython notebook without having to worry about where it's hosted. So that's where it is. And then it's shareable with other people. So I can share the link at some point with you. How do I make this go away? Okay, so the example that I'm going to use here is I'm going to build what you can call the seed of some kind of probabilistic programming language of some sort. For those of you who know what probabilistic programming is. For those of you who don't, basically I'm going to be expanding a little bit on this idea that I presented yesterday with the 3 different scripts and then simulating interventions on those 3 different scripts. So what happens if I have these scripts and I interfere with them, and then how can I study the behavior of those scripts? But I'm going to do it in a way that allows you to then programmatically explore what a counterfactual means, or what sampling from a structural equation model would look like. So if I have a structural equation model, which is this simple one, x equals epsilon 1. So f1 here is just depends on epsilon 1, and it just outputs epsilon 1. And y is x plus epsilon 2. And epsilon 1 and epsilon 2 are noise terms. I can write that in Python roughly like this. So hopefully I can evaluate these cells. Yes. So I just import randan, and epsilon, which is a vector of epsilons. So I'm just going to call it epsilons. It has multiple elements. So I will say x equals epsilon 1. I'm just going to say x equals epsilon 0 because Python is 0 indexed. And then y equals x plus epsilon 1. So this Python script that has one line for each of the variables in your model, and each line just instantiates one of these variables, given variables that you already instantiated, is kind of the Python representation of a structural equation model. But if I do it this way, it's going to be very difficult to kind of manipulate this code. So I'm going to, instead of writing them as a script, I'm going to be using a data structure. And I don't know who's familiar with order dictionaries in Python. Okay, who's familiar with, probably everybody's familiar with dictionaries. I can assume that. Order dictionary is a dictionary where the ordering matters. And I'm going to use order dictionaries because the ordering of structural equations matters. For example, if I'm going to store these functions in a dictionary, and if I don't remember the order in which these 2 things came, then why is there a dot there? Oh, it's just something weird. So if I don't remember the order in which they came, then obviously I get a different equation. So here is what I'm going to do. I define these 2 functions, f1, which depends on all the epsilon, all the vector of epsilons, and it simply returns the first epsilon. So this is the equation that instantiates x. And f2 also depends on the vector of epsilons, but now it also depends on x, and it returns x plus epsilon 1. Who doesn't know what this star tar KW args does? Don't be shy. Okay, so essentially what the reason this is here is if you want the function to not freak out when you give it arguments that you didn't specify, then you can just put this there and it's going to ignore. So if I call this function with not just x, but I also give it z or something else, then it's just this function is just going to ignore it. If I don't put it there, then it's going to complain that it got an unexpected argument. And now my model is an ordered dictionary, a list of tuples, list of pairs, and each entry in this dictionary is going to be the name of a variable and then the function I use to instantiate it. And the name of another variable and the function that I use to instantiate that. So this is my representation of that two-line script, but in this ordered dictionary format. Are people following this still? Okay. Ignore most of this documentation. So yeah, don't ignore the text because then you're not following what I'm saying. Just this is there. If you want to follow along at home, then you can read the text. So I can write this with lambda expressions. So this is a little bit kind of verbose. I'm defining and naming this function as f1 and f2. I don't really have to give names to these functions, so a more compact way to write this in Python is to use lambda expressions. So I'm going to say I'll have a variable x, and its value is going to be determined by this function. So lambda just means that this is now a function that doesn't have a name, whose inputs are epsilon and, again, these star KW args to ignore everything else, and its output is epsilon 0. So this lambda function here is going to be what corresponds to f1 here, but instead of writing it in this form with returns, I'm writing it compactly in this form. So for those of you who don't use Python very much, this is a thing you can do. So this is exactly the same as I had before. So if I write this down and then I evaluate this, and I'm calling this model 1 because I'm going to have model 2 later. So I can see that this is an ordered dictionary which maps x to a function that is a lambda expression and a function and y to another function which is a lambda expression. Of course, like the Python doesn't show me inside those functions. Okay, so one of the things that I can do is sample from a model, and I'm going to just delete all of this. Risk it. Why can I not delete all of this? Okay, so I'm going to delete all of this and rewrite it. So this is a function that takes a model in this ordered dictionary representation and potentially takes an already instantiated value of the noise and produces a sample from the model. So what I'm going to do is, if you don't give me an epsilon, then I'm going to just draw an epsilon randomly. So if epsilon is none, then epsilon equals rand n. And I'm going to say this function will only work with functional equation models that have up to 10 epsilons or up to 10 functions. So let's just arbitrarily constrain it, don't overcomplicate it. So if you haven't given me an epsilon, then I'm setting the value of epsilon to this. And now what do I do? I have to walk down the equations and I have to actually calculate the value of those. So I'm going to do sample. So I start with an empty sample. The sample is going to be a dictionary that maps names of variables to their values. Initially, I have no variables instantiated, so I start with an empty dictionary. And then I go for variable function in model.items. So I just iterate over the items in this model, each of which has a variable mapped to a function. I will say, so I call function. So this is now going to be a function that you can call one of those lambda expressions, for example. And this function, I call it with a I have to give it epsilon. So remember that all of these functions expect epsilon, the epsilon vector, to be their first argument. And then I'm going to do this. What this does is it looks up this dictionary sample. It maps the names of the variables to its values. So if I go star star sample, it's essentially going to go through all of those variables and give it to this function as its keyword arguments. And then I'm going to evaluate this and then store it in my sample. And then I'm just going to say return sample. Okay. So hopefully some people, or most of you, have followed this. This is a way in which I take a model in this form and I sample from it. Now I actually created a test. So this is a test that with a fixed random seed actually knows what to extract from the function. So I'm just going to test if my implementation is correct and it passes. So just making sure that I didn't make a mistake. This is, by the way, great. This is why we like test-driven development, because you kind of want to know that if you change something that you didn't actually change what the function does. Okay, so I can do this. I fix the random seed to 2019, and then I say first sample, and then I print a sample from this model, and second sample, print a sample from this model. So each of these samples is going to look like this. It maps X to its instantiated value 0.21 and Y to its instantiated value 0.60. And we can look inside this function of how this actually happens. So I can go print sample at every single step in this for cycle. And you're going to see that what happens is that you start from an empty sample where none of the variables is instantiated. Then the value of X is set. And then this value of X is passed on to the function that computes Y, and finally you get both X and Y in this way. All right, so now you can play around with this in various ways. So for example, I already did this. I can I just created a function that plots the joint distribution of samples, joint distribution of X and Y from this. What it does is samples from the model. So model is one of these ordered dictionaries. You call sample from model num samples times, which is a number like 100 times. This is a Python expression to essentially it's like a for cycle to repeat this 100 times. And then I'm going to just use Seaborn. I don't know if people use Seaborn, but it's like basically just makes their plots more beautiful. And it does a lot more than that, but if you just do import Seaborn, then your just plots are automatically nicer. And so I'm going to use Seaborn's joint plot, which is going to plot me the scatter plot alongside these histograms on the two axes. So I'm going to execute this, and this is what I get. So this is the joint distribution of X and Y. Any questions so far about this? Also, by the way, I set it to poster, which automatically increases the font size, which is pretty cool. All right. So now, what are the things you can do on a functional structural equation model? This is kind of the cool part, which is now we are going to an intervention is something that you apply to this set of equation, and out comes another set of equations. So intervene is going to be a function that takes a model and the set of interventions, and it outputs another model, where those functions that you intervened on will be replaced by something. So let's try and rewrite this. Now this is riskier, but still doable. Okay, so this is obviously not going to pass. So what do we need to do? Well, we need to say for each intervention, so there might be multiple interventions. So you intervene and set X to a certain value, and then you also want to set another variable to something else. So you can walk through them for variable value. So I expect interventions to be a mapping of variable names to values again. For variable value in interventions, items, what do I want to do? I want to look up the function that would instantiate this variable. So let's say that if my intervention is x and 3, which would mean set the value of x to 3, I look up the function that would instantiate x, and then I simply set it to a lambda expression, a function that always just returns a constant. So I assume that all of these functions first have to take epsilon, the vector of epsilons, and then it doesn't actually depend on any of the variables. So it's just going to be key WRs. It ignores all its inputs. And then I'm going to return value. So it ignores epsilon. So notice that value is just a value that you set in the intervention. It doesn't depend on the epsilon anymore. It doesn't depend on any of the other variables. If you call this function with any inputs, it's going to return this constant that I'm given. And then I'm going to say return model. Oh yeah, one other thing that I want to do is I don't want to actually do this on the model itself. I want to return a copy of the model. So let's say new model equals model copy. And hopefully this is how it's supposed to work. So this is just making sure that that I'm not modifying the original model itself. And I don't have a test for this, but kind of a test, which is I know that with this random seed, these are the expected results. So now I can say, I can sample from the model that I get by taking model 1 and intervening by setting x equals 1. And I can then sample from it. And I get the results that I expected. So this just shows that kind of I correctly implemented this function. Does this make sense? So this is how you intervene. You take the function that previously set the value of x, and you replace it with a function that always returns a constant. Very boring, but that's sort of what an intervention does. And now you can do things with it. I can say, I already plotted the joint distribution of x and y. Now I can say, take the model that you get by intervening on this model, and then plot the joint distribution of that. And that's going to be here. And this should be familiar with you, familiar to you, because this was in the presentation yesterday. So notice that all the variables, all the values of x are now 3, because the function that creates 3 just returns 3s all the time. And then the value of y is set using the epsilons, or using the corresponding epsilons that it used before. Now I'm going to have a bunch more of these plotting functions. You don't have to understand what they're doing. So this takes a model, takes a variable, and plots its marginal. These are very dumb functions. Do the simplest thing that I could come up with to plot this marginal. So they draw a certain number of, for example, for the marginal, you draw a certain number of samples from this model, and then you simply plot a KDE plot, which is a kernel density estimation plot of this thing. And I use pandas data frames to make life easier. I can plot the conditional, and this does something weirder because so I created these samples. By the way, I'm going to show you what this pandas stuff does, because if you haven't seen it. So okay, so first thing I'm going to do is, when I do this, num samples is undefined, so I'm just going to say 10. So, yep. So if I do this, what it's going to do is it's basically just going to iterate 10 times. This is like a weird Python thing to do. But then it's going to call this function 10 times. And because we are not giving this function any epsilons, every time you call it, it creates new epsilons. It calls the randn function and creates its own epsilon, so you get random samples. So if I show you what this is, it's just you know, a bunch of these dictionaries. And notice that the values of x and y differs here. Okay, now what I can do is I can I can just create a pandas data frame from this, and it already expects data in this format, and is going to represent it as a data frame, which you can now do a bunch of things with. So, for example, I could say plot x, which is like it plots the value of y as a function of x. For example, you could do this directly, and you get this like this sort of crisscross. Or I can just do give me only x, and then you have just the axis from it. Okay, so this is what this pandas thing does. I just wanted to show you if you are not familiar. So how do I plot the conditional? I get samples, I create a data frame, and then I say, look at this samples data frame, given variable. So this is the name of the variable that you want to condition on, and I apply this function, which is essentially, it's like a little bit of a nearest neighbor thing, which is I basically filter out all the entries of this data where x is close to value, and there is this tolerance term. Doesn't matter. So because these are continuous distribution, I can't find entries where the value of x is exactly the x I wanted. I find the entries where the value of x is close to the x I wanted. And then I simply just plot the marginal distribution of those samples. So this is like a nearest neighbor type of thing. And here I'm doing the same, but with interventions. So this plots the conditional distribution. This simulates the intervention and plots the intervention, the py given do x kind of thing. Okay, so I can do these things. I can plot the marginal of y, for example, in model 1, and it's going to have a 0 mean, it seems, and some variance around it. I don't know how to make it smaller. Maybe if I set it to paper. Yes, now you get smaller things, but you also can't read the axes anymore. And then I can plot the conditional of model 1, conditional of p of y given x equals 3. This is how my function works. So you can play around with this, and this is going to be this is going to take some time because it creates a lot of samples and then filters and creates this pretty lame and we know this is supposed to be a Gaussian because we only use Gaussians. It's kind of approximately that. Now I can actually run the intervention and plot the intervention conditional. And this is what you get. And you observe that in this particular case, the two are the same. So p of do x given, this is p of y given x, just a conditional. This is the intervention conditional p of y given do x equals 3. And in this particular graph, you expect these two to actually coincide, so it's fine. Okay, what else can I do with this? Okay, so here I've come. So these are the basic primitives that I do with these things. I have the intervention, and then I can sample from the models. And now I recreated the examples from my talk, but I write them in this form that this script accepts. So first here. I don't know if I want to go through this, but essentially these are the same things that I had on the screen, except that I now have it in this ordered dictionary format. So these are the if you remember, this example had 2 lines and 2 lines, and the third example had 3 lines. So I have, and the third example had z. So here I have the third structural equation to describe z as well. So I can just create these. I call them xy, yx, and conf, where conf is a confounding variable. And now you can verify in this that if I draw a joint distribution from model XY, or if I draw, these are actually how I created the plots for the talk. If you draw it from model YX, or if you draw it from the third thing, then you're gonna get exactly the same results. So you can sort of visually inspect these if you put them side by side. Now, one thing that I can also show you, that if you run, say, a statistical test. So here I run a t-test, which tests if the mean of the random samples are the same. I use 10,000 samples, or sorry, 1,000 samples, and I sample from model XY and I sample from model YX. So I have two sets of samples, samples 1 and samples 2, and then I run a t-test on these two samples. So if the samples that I get from the two models were different, had a different mean, I would expect a p-value to be small, which is when they would be statistically significantly different, and the p-value is high, indicating that a t-test cannot distinguish between the means of the two data sets. So this is just showing you that indeed these models create statistically significantly the same, I don't know if you can say that, distributions. So they are indistinguishable if you only look at the samples that you draw from them. And then now you can see how these different models actually behave under intervention. So now I'm plotting the joint distribution of intervene model XY, x equals 3, and I'm setting the y limit on the axis to make sure that I expect the distribution of y to shift, so I just want to make sure that that it's drawing the same y-axis on all of these plots. So I'm gonna do the blue model, the green model, and the red model. And as you've seen in the slides, for the blue model, you actually get something that has a mean around 5 or 4, and for the red model, you get something that has a mean around 1, and for the green model, you have something that has a mean around the green. In order to plot these, I actually simulated the intervention, which is the equivalent of running the randomized control trial, or running the experiment and seeing what happens. And now the whole point of do calculus is that I will be able to predict that these systems work differently under interventions without ever using the intervene function. That's the point. So if I can use the intervene function, the real world equivalent of that would be I can actually run an experiment. If I'm not allowed to use the intervene function, I have to use causal inference and do calculus to estimate the quantities. So here I'm just plotting the conditional distribution of y given x equals 3. And of course, all of these three are going to be lining up on top of each other. I'm going to execute this so it's smaller. This is taking forever. Okay, so here I actually simulate simulate p of y given do x, which means that this plot intervention conditional is a function that used intervene inside. So this is like running the experiments, and I see that if I actually run the intervention and then I look at the conditional distribution of y given x, these models behave differently. The red and the blue, red and the green work the same way, but the blue works differently. But now I can come to the same conclusion without actually using the intervene function. So if you remember, the analysis said that do calculus tells us, based on the graph structure, that if your model structure is y, x, an arrow pointing from x to y, then p of y given do x, p of y given do x corresponds to p of y given x. But if the arrow is the opposite direction, so now y leads to x, or if the situation is consistent with the confounder z influencing both x and y, in these cases, the P of y given do x corresponds to the marginal distribution of y. If you remember, if you cut the edges, then the y and the x become independent. And so you just get the marginal distribution of y. So I know that if I plot the conditional distribution of model xy and I put the marginal distribution of model xy and model yx and model conf, then I'm basically done. And notice that these functions don't use the intervene inside. This basically just plots the conditional distribution and the marginal distribution of this model. Never do any interventions. And I was able to correctly predict if this is ever going to return anything. I was able to kind of plot this P of y given do x equals 3 even without actually running the intervention. So that's the full story of that example. And then you can play around if you want to create these structural equation models with more than 2 variables or more than 3 variables. And for example, you can recreate one cool thing would be if you would recreate the lung cancer example, the smoking tar lung cancer example, and actually tried to do this with the backdoor adjustment formula, which I was briefly flashing on one of the slides, but I haven't talked about. Okay, so another thing that was on my slide is the explaining away. This is about collider bias. So remember, this was the example where you have coding ability and you have people skills, and then we hire people who have either good coding ability or good people skills. So the toy example corresponding to this is that X, say coding skills, is instantiated by this function that just takes epsilon 0, so the first random noise variable, and then independently we draw y also to the second epsilon, and then z, which is the hiring decision, is going to be dependent on x and y. It's going to say, I'm going to do, it's not exactly the example from the slides. I'm going to say if x plus y plus a little bit of noise, 0.3 times the next epsilon, so this is epsilon 2, which is the epsilon available to this function. If this sum is greater than 2.5, then z is going to be true. So z is a binary variable, x and y are x and y are real valued. So what I'm going to do here is I'm just going to, okay. So I'm going to sample from model. I'm actually just going to copy this. So I'm going to sample from the model n times. 100 times. Okay, invalid syntax, great. Epsilon, oh, yes. It's actually very weird when the characters are so big on your screen. I'm just looking for excuses. So this is observations, and then I can say pd.dataframe observations.head, which is just going to show me the first few examples from this data. So we can see that x and y are random variables that are continuous, and they are actually the epsilons, so they are normally distributed. And then z can be either false or true. If I ask for more examples, maybe I'm going to see a true example. Oh, this guy, yes. There's one true example in this. And so now I'm going to be able to do this. So I'm just going to call this data. And then I'm going to say data, where data z, or z equals true. This is just going to what this does is this essentially filters this data database, whatever, to only keep the values where z equals true. So this is essentially conditioning on z being true. I can do that in pandas by doing this. And if I have a few more of these examples, then I'm going to be left with maybe more than three examples. So now this is after a sampling bias. So after I only consider the applicants that I actually hired, I can look at what the joint distribution of x and y looks like. So let's consider the plot joint model explaining away x, y. I actually forgot the syntax for this. So I'm just going to draw the 1,000 samples here. So you can see that if I don't condition on z, this is just plotting the joint distribution of x and y in this model, I can see a nice independent distribution. But if I now say SNS.joint plot but if I now plot only the stuff that's left after the filtering for z equals true, now I see a negative correlation. And this joint plot is so nice that it also automatically calculates this Pearson correlation and the p-value. And the p-value is very small. It's 10 to the minus 9 times something. So this means that there is statistically significant negative correlation. I mean, you can see it with your eyes between these two variables. So this shows explaining away, and this shows collider bias. If you accidentally or willingly condition on a collider variable in a network, so something that depends on both x and y, then this can introduce a spurious correlation, a spurious negative association between the variables. Sampling bias, by the way, is one of the most difficult things to deal with, because if you wanted to build tools that deal with it, you would kind of have to know about all the data that is not in your data set. Like, in order to be, either you have to have a model of the sampling process, or if you don't have a model, then you have to know or make some assumptions about what are the data points that are missing from your data set. And those assumptions are very hard to make. All right. People are falling asleep. Great. Job well done. It's actually good because you haven't been drinking alcohol yet, so you're actually going to have some NREM sleep, which is when memories are forming. So I actually recommend everybody to sleep before you drink, because then you actually have a chance of some of these memories that you're making, then making it into long-term memory. Okay, so another thing that I wanted to show you was, and I'm starting to slow down myself, is how you can then deal with counterfactuals, which is what we talked about today. So as I said, the trick with counterfactuals is that you share the epsilon in the two models. This is why I allowed my sample from model function to take in a predefined epsilon. So that I can do this. So I say, I want to create n equals 1,000 samples. So I start with, I know that I'm going to need 3 epsilons for this model. So I'm going to create n times 3 epsilons. N equals the number of data points. 3 equals the number of different epsilons. So I create this, and then I say, for every epsilon, for every particular epsilon vector in this epsilon's matrix, so this just walks through the rows of the matrix, I'm going to plug this epsilon into this model explaining away. So this is what I get, observations. I'm going to walk through the same epsilons for epsilon and epsilons. I'm going to plug that into the sample from model function, but instead of using model explaining away, I plug it into this intervened model, where I intervene and set x equals 2. So I want to now ask questions about, if my coding ability was 2, whatever that number means, would I have given the job? Would I have been given the job? Questions? No. So I call these twin data points. And so this is where basically my thing ends. You can basically say observations and head. And this is going to just show you that you have obviously random samples, but I can do this if it works. I never actually tried. I can concatenate this to look at the joint distribution of them. So I'm going to concatenate these two tables. If anybody sees that I'm doing something stupid, then just tell me that I'm using the wrong syntax or something. Twin examples, twin data points. So I can't type anymore. So basically this this is going to be another set of observations which contains the evil twins of the people who are in this thing. Merge. Data points. Ah. You can see where I'm coming from. That's a good one. Data points. That's actually a very good name for a meetup. Data points. Pretty sure that somebody's come up with it. Okay, this is. It's not concatenate? It is concatenate. Okay. 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 Now I'm gonna try a few times and then I'm just gonna give up. Nope. Or just concat or something. All right. Pandas.concat or nope. Okay, last try. And then you're free. What is it? All right, okay. I can't figure out the syntax for this. I wanted to concatenate the two data frames so that I can show the joint distribution. Does anyone know how to do that in Pandas? pd.concat? Yes, okay. Amazing. Thank you very much. Oh, but I want to merge. Sorry. No, that wine estate looks more and more. All right. This is where I'm going to end. Basically, you can imagine that if I manage to concatenate those two tables together, essentially I wanted to join them. So I wanted to see the columns next to each other, and I'm pretty sure that after a further 45 minutes, I could have maybe figured out. And then you could see that they obviously have a non-trivial joint distribution because I fed the same epsilons into both simulators, both equation models. So now you could technically do stuff like fit a machine learning model to predict the x's in the twin data points from the x's and the y's in the observations, for example, or x's and y's and z's in the observations, and those would then start modeling the conditional distributions of that would correspond to the counterfactuals that we talked about today. But I'm going to stop here. I'm going to finish this example and send and then also write some documentation so you can follow along if you want to maybe do that after you go home after the summer school, and if you find this a useful way of thinking about it and seeing what happens. You can do all sorts of random interventions are an interesting thing to try, which is instead of setting it to a constant, you set it to a random distribution and see what you will get in that under that constraint. Any questions? Otherwise, I'll close. Any questions? Okay? Well, off you go. Thank you.